Okay, since recording starts now, let me introduce myself again. I am Hojun Lee, the president of EQS and Journal Club manager of QISCA. It is my pleasure to introduce today's Journal Club speaker, Hojun Lee from EQS. Hojun has recently completed his master's degree in the Quantum Information Theory Lab in the School of Electrical Engineering at KAIST, which was led by Professor Junwoo Bae. Also, he was the former president of EQS. Today, he will be presenting a talk titled Quantum Error Correction, Color Code and Transversal Gates, sharing insights from the paper Universal Transversal Gates with Color Codes by Kubica et al. And Gauge Color Codes by Optimal Transversal Gates and Gauge Fixing in Topological Stabilizer Codes by Bombín et al. Please join me in welcoming Hojun to the stage.
Hello, my name is Hojun Lee from KITE EQS, and today I will talk about quantum error correction, color code, and transversal gates. And this presentation is based on the paper in the bottom. And if you have any questions during the presentation, please ask me anytime. And first of all, I'll talk about why quantum error correction is needed. In real world, quantum gates are noisy, which means it could operate in unwanted way. And if we compute with these noisy gates, the computation result might be faulty. So we add redundancy for quantum information to make them correctable against errors. And let's consider the following scenario. Here, we encode k logical qubits into n physical qubits, and suppose an error occurred in the encoded logical states. The redundancy allows us to detect which error has occurred, and we can recover the state by applying the inverse operation. And there are special class of quantum error correcting code named stabilizer code, and most of the codes used in quantum computing are stabilizer code. And for stabilizer codes, we can measure error syndromes to figure out which error has occurred. Now I'll explain about the stabilizer formalism. And we can define a code by defining stabilizer group, which is the subgroup of the Pauli group. And the code space is a simultaneous +1 eigenspace of stabilizers. For example, if the stabilizer group is generated by ZZI and IZZ, then the code space will be the linear combination of 000 state and 111 state. And you can verify by multiplying these stabilized generators at these quantum states. Actually, stabilized by ZDI means that the first qubit and the second qubit are the same, and IZZ means the second and third are same. So only 000 and 111 states left. And note that the stabilizer group is abelian because otherwise there will exist two stabilizer generators that are anti-commutes, and no co-states will satisfy the stabilizer condition. And for the case that error happened, we measure error syndromes, and for each error stabilizer generator G, we measure G, which is equivalent to projecting the state into the eigenspace of G. And if the result is +1 and it's not a problem, and we can let the syndrome as 0. And if the result is -1, this could not happen for cold states. So it means an error occurred, and we'll at the end we get a bit string of syndromes, and we can determine which error has occurred if the different error have different error syndromes. Is there any questions?
Yeah, I have a question.
Yeah.
Can you also define stabilizer states for qubits or qubit systems, like for general qubit systems?
I don't know about the not non-qubit systems. Sorry.
Yeah, I'm asking this because there's also recently a bosonic quantum error correction as that's an active research field.
Sorry, can you say again?
So recently there has been a lot of studies on bosonic error correcting codes, and obviously bosons are not qubits.
Yeah. Then they might be not a stabilizer codes. Oh, okay. I'll continue. Now I will introduce color codes, which is also a stabilizer codes. And first, let's consider a tiling of the sphere. And figure A is a tiling of a sphere, where the outer circle is identified as a vertex V. And you can imagine that put this figure on the sphere and stretch the outer circle so that it shrinks into a point. And this tiling should satisfy two conditions. And every vertex is three-valent, which means it is connected with exactly three vertices. And every face should be three colorable, which means every adjacent faces should have different colors. Then remove the vertex V, which is the outer circle, and three faces that contains V, and three edges that contains V. Then it becomes like figure B. And then place qubit at each vertex. And for each face, add all X stabilizer and all Z stabilizer. All X stabilizer means that the product of all vertices on a face, and X for all vertices on a face, we add X. This one, this one, this one. And to make this code well defined, we have to check the commutativity between every two stabilizers. If two stabilizers are both X type or both Z type, they are trivially commutes. So let's consider the case that one is X type and another one is Z type. And from the three valence and three colorability, we can know that every two face, for every two face, they are disjoint or share even vertices or identical. So for disjoint case, the stabilizers commute. And if they share even vertices, they also commute because if you change X and Z even times, then the sign will be +1. And for the case that both stabilizers come from the same face, they also commute because in color codes, every face have even vertices. Now let's think about the logical dimension of this code. If there is no stabilizer constraint, the dimension will be 2 to the v. And for each independent stabilizer generator, the dimension divided by 2, the states with eigenvalue plus 1 and the state with eigenvalue minus 1. And for this case, there are 2 times f stabilizer generators. So we can say that they are v minus 2 times f logical qubits. And let's add one vertex and 3 edges temporally, like figure A. And since it's 3 valence, 2 times of number of edges equal to 3 times of number of vertices. So we can get 3 plus 1 equals 2 e plus 3. And from Euler's formula, v minus e plus f equals 1. And we can deduce that v minus 2f equals 1. So this encodes single logical qubits. Is there any questions? If not, I will continue. And one famous example of color code is the Steen code, which is in the right figure. There are 3 phases, so there are 3 X-type stabilizer and 3 Z-type stabilizer. And there is 1 logical qubit because 7 minus 6 equals 1. And Steen code can correct any single qubit errors. For example, if x2 error occurs, then the Z-type stabilizer of blue phase and green phase will detect this error. And if Y1 error occurs, you can think that both X1 and Z1 error occurred. And blue X-type and blue Z-type stabilizer will detect it. And it's known that if we can correct any single qubit Pauli errors, then we can correct any arbitrary single qubit errors. So we just have to consider Pauli errors. And once we encode the state into logical states, we need logical operators. And of course, the stabilizer condition should be satisfied after applying the logical operators. And this is the sufficient condition of logical operators. For this stabilizer group generated by S1 to Sm, if L inverse Si, L belongs to the stabilizer group for each I, then we can say that L is a logical operator. And this is the proof. Let's check that any L psi satisfy the stabilizer condition. And first we multiply Si to the L psi, and then we multiply L inverse at the left of the formula. Since L inverse SIL is also a stabilizer, it vanishes, so it becomes L psi. And this means L psi is also a logical state because it is stabilized by arbitrary stabilizer, Si. Converse is not true. Yeah, converse is not true. And for the Steen code, we can let logical X and logical Z operator as all X and all Z operator. For example, logical X operator commutes with any stabilizer generators. So XL inverse SI XL equals Si, which also belongs to the stabilizer. And note that logical X and logical Z operator anti-commute. And it is well defined because real X and Z operator also anti-commute. And there is a good class of logical gates named transversal gates. And consider the case that each logical block has n physical qubits, and they are m logical blocks. And the operation F is called transversal if F is a product of GIs, and GI only acts on ith qubits on each blocks. For example, thin code has transversal logical Pauli gates. Since Pauli gates are single qubit gates, we can let m be equal to 1. And for example, logical X operator is a product of SIs, XIs, and GI is XI for this case. And note that transversal gates do not have multi-qubit gates within a logical block. Then why transversal gates are good? Until now, we assumed that errors only occur after encoding logical states, and there are no errors in syndrome measurement, error recovery, and logical operations. But in reality, errors may occur anywhere. Errors can occur before the logical operations or during the logical operation. And if there exists multi-qubit gates within the logical block, error propagates through the gate. For example, if a Pauli X error occur before C naught at the control part, it is equivalent to the case that X error occur at both control and target part after C naught gates. Steam codes can correct single X error, but cannot correct XX error. So we don't like this situation, like the weight of the error increasing. However, transversal gates do not propagate errors. Like Steam code, color codes have transversal logical Pauli operators. And since every phase have even vertices, all X and all Z operator commute with any stabilizer. So all X and all Z operator can be the logical X and Z operators. And color code also have transversal logical C-NOT gates. And suppose there are two logical blocks and we want to apply a logical C-NOT from the upper block to the lower block. Then all we have to do is applying C-NOTs from each qubits of the upper block to the corresponding qubits of the lower block. Since these C-NOTs only operates on ith qubits of the blocks, we can say that this C-NOT gate is transversal. Now let's verify that this logical C-NOT gate is actually a logical operator. And then let's show that it acts as a C-NOT gate. And this is a commutation relation between C-NOT gate and Pauli operators. And for any stabilizer generator of form SI tensor identity, if SI is X type, and this conjugation becomes SI tensor SI, which also belongs to stabilizer group. Note that C-NOT inverse is also a C-NOT. And if SI is Z type, this conjugation becomes SI tensor identity. and is also belongs to the stabilizer group. And this also works for identity tensor Si case. So this logical CNOT is a real logical operator. Do you have any questions?
Okay, I have a question.
Okay.
Given a logical code, can you always verify whether you have a transversal logic gates?
If you can find the transversal gates, then it implements the transversal logical gates, but I don't know how to verify that if there exists transversal gates. There's some known results that some special class have some transversal logical gates. For example, CSS gates have logical transversal CNOT gates. And color code also.
Okay, thank you.
Okay. And I'll continue. And let's verify that this logical CNOT act like a CNOT. And you can see that these commutation relations also satisfy the logical CNOT and logical Paulis, because logical CNOT, logical X and Z are just a products of CNOT X or Z. So this relation will be satisfied. So we can say that this product of CNOT is also a logical CNOT. And color codes also have transversal logical Hadamard gates. And logical Hadamard gates can be implemented just by the product of Hadamard gates. And note that H inverse XH is equal to Z, and H inverse ZH is X. So the conjugation with Hadamard interchanges X and Z. For the X-type stabilizer S, HL inverse for the X-type stabilizer S, let's consider the conjugation with HL. And for the qubits not belongs to S, and this will be it just becomes identity. And for the qubits belongs to S, and then it will change into Z. So, and all Z operators on the same phase is also a stabilizer. And this also works for the Z-type stabilizer. So we can say that HL is also a logical operator. And since logical Hadamard is a product of all Hadamards, it also follows the commutation relations. So this operation acts as a Hadamard. And finally, color codes have transversal logical S gate. S gate is the square root of Z gate. And the vertices of color codes are bipartite, which means we can divide the vertices into two sets, T and T complement, and only vertices from different sets have edge. And for some integer k, apply S to the k at the qubits belongs to the set T, and apply S to the minus k at the qubits belongs to the set T complements, and this implements a logical S gate for some integer k. First, let's show that this operator U is a logical operator. And note that S inverse is I xt, and S inverse xs is minus I xt, and S operator Z commutes. And we can deduce that skx x s to the k x s to the minus k equals to I to the k x z to the k, and s to the k s to the minus k x s to the k equals minus I to the minus k x z k. Here we use that z inverse z to the minus k equals z to the k. And since every phase have equal number of qubits that belongs to the set T and the set T complement, this phase vanishes. So U inverse XF U becomes the elements of the stabilizer group. And also U inverse CF U belongs to the stabilizer group. So you can say that U is logical gates. And since color codes have odd number of vertices, T minus T complement is odd. So, and let the K be T minus T complement. And this commutation relation can be calculated similarly as the previous slide. And since K is T minus T complement, K times T minus T complement becomes 1 modulo 4. So you act as a S gate. We saw that color codes have transversal logical Pauli gates, CNOT gates, and Hadamard gates, and S gate. And we say that the group generated by these gates as Clifford group, but we need a gate outside of the Clifford group to achieve universal quantum computation. For example, if we can implement all Clifford gates and T gates, we can implement arbitrary quantum computation. Then, do you think is it possible to make universal and transversal logical gates? The answer is no. Due to the Easton-Neal theorem, there are no codes that have universal, transversal logical gates. Then why just we only use the Clifford gates? According to Gottesman-Neal theorem, the quantum circuit consists only of the state preparation in all zero states and unitary operations from Clifford group, and measurement in the computational basis can be efficiently simulated by classical computation. So we need alternative approach to implement non-Clifford operations. And one of these methods is magic state distillation. We call this A state as a magic state, which is T plus states. And if we can prepare A state, we can implement T gates. And magic state distillation is distilling high fidelity logical magic states from multiple noisy logical magic states. In conclusion, transversal gates play a key role in fault-tolerant quantum computation, and color code allows transversal implementation of all logical Clifford gates. But due to the Easton-Neal theorem, we need alternate approaches to achieve universal quantum computation. Thank you for listening my presentation. Is there any questions?
Okay, so what is the general distance of a color code?
Maybe it is the length of the disk. Length of the disk.
Length of the triangle.
Triangle plus 1. So number of the vertices in the one side.
Okay. And compared to toric codes, or these color codes have any advantages compared to toric codes or surface codes?
So you mean that there is any advantage of color codes than other codes?
Yes, right.
This transversality is the major advantage because it does not propagate errors. Maybe surface code or not other codes have complicated implementation of logical gates, but this is simple. And someone asked me that this color code should be implemented in two sphere. I don't know about implementing this in torus, but if we encode this in 3 sphere, one higher dimension, then we call this as 3D color codes, and instead of this, it may have transversal T gates, but it cannot implement H gates, so it is not. It also meets this Easton theorem.
So you're saying that 3D colored codes have transversal logical T gates?
Yes.
Yeah, but T gate is not a Clifford gate.
Among this presentation, I only consider 2D color codes, and 3D color codes have different set of transversal gates.
Okay.
C는 그런 삼각형 있잖아요. 그거를 4개 붙인 거라고 생각하면 좀 들어요. 그거보다 왜 저구조보다 조금 더 하나 늘려서 하는 의미가 있는 건지.
잠시만 다시 한번.
그 C는 코드였나요? 그 있잖아요. C는 코드
네.
이거를 4개 붙이면은 되는 것 같은데. 그 C는 코드 4개를 붙이면 되는 것 같은데. 네. 9개 붙여거나 더 굳이 4개를 붙이지 말고 더 하이어로 붙이지 않는 이유는.
Someone asked that why don't we use more bigger color codes? Actually, it's also a color code, and you can use that code. It has different distance. Yeah.
Okay, I have one more question.
Okay.
What is the threshold probability of a color code? Like for instance, for surface code, it's like 1 to 2%. What about for color code?
I'm sorry, I don't know.
Okay.
If there's no further question, thanks Hojun again. And we would like to conclude today's introductory seminar and journal club. Thank you.